Okay, welcome back. So we're thinking about geometry again today. We're talking about congruent triangle proofs. And the reason we're sticking with this is just to keep emphasizing the importance of the kind of underpinning logic here. As you move forward past this class, it's going to become more and more important, in particular in college classes, that you recognize what underpins a lot of the mathematics that you're doing. So it's not simply calculations or procedural, but it's much more like what is the point here and what is the reason that we're doing. So there's statements and reasons, as we know, there's givens, there's proofs. All of this is going to be important and gives us a language to really talk about many things. So let me label here. And so it's a classic setup. We seem to have two triangles and kind of like a butterfly or bow tie type shape. A couple of given statements here. All right, so what do we have? We have BC congruent to DC, and we have AC congruent to EC. So hopefully at this point you're seeing it. Hopefully at this point you are seeing what we're talking about here. We're trying to prove that triangle ABC is congruent to triangle EDC. Now, what is the logic? Again, we use our postulates, the ones that work, and the ones that work do so because given a smaller subset of information, they only admit to one triangle, right? So if you know these pieces of information and you were to complete the triangle, there's only one possible way to do so. And therefore, knowing these pieces of information to be congruent across two triangles, then they both admit to the same one, and therefore they're congruent. So what do we have here statement-wise? Well, we start with our givens, per usual. And now what we know we want to establish that the two triangles are congruent, and we're likely going to do that via one of the postulates. And this is where the diagram comes in helpful. You can kind of start to see, like, well, what are our options here? Well, we can prove that the remaining sides are congruent, like AB and ED. But I don't really have a reason to say that they're congruent. They might look it, but I can't really tell why. We know there's a problem if it's an external angle to two side congruences. So the fact that we have side-side leads me to either side-side-side or side-angle-side, not side-side angle, right? The problem with that being we can actually admit two different triangles with that situation. So side-side-side seems a little tricky. What about side-angle-side? I think the first thing to recognize is, can you identify what angle we're talking about when we talk about the side-angle-side postulate? Given the setup we have, we're talking about this and this. And why are those two angles congruent? Well, vertical angles. Okay. Let's look at another one. I guess we can reset. The easiest. Let's get out our ruler. Remember that the diagram, even when it's given to us, and even when it might look to be intentionally perfect, we don't want to necessarily rely on the diagram as the proof itself. The diagram is illustrative of the statements about it that are in more abstract terms. So let's label here. And we'll start with our givens. And this is the thing about all of this. So the given statements are establishing a set of circumstances. So if we understand and can commit to the idea that these postulates let us go from a smaller amount of information to saying, well, these must be the same identical triangles in different positions, we are actually then just kind of pairing off layers from those postulates and saying, well, what pieces of information could we not be given and actually have just be a result of the coordination of the pieces, like in the previous one, that those two angles are vertical to each other, so they're congruent. So it's really a system of saying, here are your postulates. Now let's take a few pieces of information away, or at least that we know those pieces of information away. What might we be looking at? What kind of situations might we be looking at? So here we have a couple of pieces of information that we are told to be true. JK and LK are congruent. JM and LM are congruent. So what are we looking at here? Well, JK, LK, okay, JM, LM, those are congruent, okay. And you hopefully can see what we're going to try to prove. Sometimes there's more than one that's possible, so you do want to be very careful. But don't discount your intuition on these ones where there's only two real triangles to be talking about. Of course, we're trying to prove that they're congruent. Maybe they're not, right? So we always want to admit the possibility that the task of proving, and it might not actually be true, right? So maybe they're not congruent. But if we're trying to prove that they are, let's dispose our tools, right, in the right way here. Let's utilize them. So can you see it? Can you see the two triangles? Can you see how they're congruent? Here's triangle 1, triangle 2. Trying to say that they're congruent to each other. Can we see why? Well, this is going to use the side, side, side postulate, right? I mean, what are our options? Really only side, 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 and side, angle, side at this point, because we have two sides known to be congruent to their corresponding pairs. Side, angle, side seems a little tricky here, right? We don't have any information about the side, about the angles. They don't seem to relate in any obvious ways, because we're not told, for example, that like KM is a bisector. Even if we were, that would be the exterior angle. So we're really thinking about like the angle KJM and KLM, those pairs, that pair. So yeah, I'm not seeing it. I'm not seeing why we should be convinced or be able to convince ourselves that those two angles are congruent. They certainly might be, and if the triangles are congruent, then they are. But without that result, I don't know how to be sure that those angles are congruent directly. On the other hand, the third side to these two triangles, which is KM for both, absolutely feel like that is congruent. Right? It's the simplest for me, it's the simplest reason to be congruent. Even more simple in a lot of ways than something that's given, because given we have to suspend, any sort of calculation or measurement. We're just told these things to be true as assumptions or as givens. But this Km congruent to Km statement, very, very useful, right? The reflexive property. Something is congruent to itself, and that becomes incredibly useful precisely right now, when that same thing is a part of two different things, right? Part of two different triangles. Okay. All right. Another good one. Let's do one more. Looking through some of my examples here, so I think this will be a good one. All right. Kind of looks like a kite setup. Let's give ourselves some labels. That'll be point F, that'll be point G, point H, point I. Okay. All right. What are we given? We're given this. That's right here. And we're also given that the line segment FH bisects the angle GFI. So a couple things that we need to recognize. Can we identify the pieces? Can we see the angle GFI? What angle are we talking about? We're talking about this angle right there. And we're talking about the line segment FH cutting across right there in the center of this kite diagram, and it specifically bisects. So it doesn't just cut it, it bisects the angle. What does that mean? Well, it means something very precise. Okay, bisection means that you're cutting an angle or a line segment in equal halves. So let's see. Okay, so what do we really want to say next? Well, let's look at our diagram here. So we have the two kind of opposing angles, G and I, are congruent to each other, and then we have this kind of internal line segment bisecting this other angle, GFI. So the bisection creates something that we need to state, that the angle GFH is congruent to the angle IFH. By the definition of angle bisector. Remember we talked about this a few lessons ago, these types of statements that we need to understand, that the terminology that actually is very technically important, like bisect, what that means. Further, so now let's stop right here for a second. So, okay, by definition of the angle bisector, we get this kind of evolution from the given statements where instead of just two angles congruent to each other, we actually get two more angles congruent to each other via the bisection. And we see the triangles starting to take shape, even though they're previously stated and we could identify them in the first place, these two triangles. Then we don't ever want to overlook the simple thing that's staring us in the face about those two triangles, which is that they share a side. Very powerful, very important. Something is congruent to itself. And that's all we need. That's all we need in this case. So we're doing these again and again in order to illustrate something important. That we can do this set of logical steps where we take things that are given and we infer from them. We say, okay, well, if these two things are true, then this also has to be true. And if this is also true, then this also has to be true. And so there's this progression of steps where we start from a couple of facts and we evolve out from them using this logic, deductive logic. So often what we're using are definitions, so things like a defined word, like bisect. We're using kind of common sense properties like reflexiveness, that there's a kind of inherent property that something is congruent to itself. And importantly, we're also using these three-piece postulates where we look at if we know pieces about a triangle are congruent to another set of pieces about a different triangle, then from there we can infer that those are the same triangle because they only admit to one, right? And just to reiterate something from a prior discussion, we know that knowing three angles are congruent to each other is not enough to saying that the triangles are congruent, that there's something else going on here. The idea of similar triangles. It's a weaker proposition than congruency. Congruency says not only do they have the same angles, they also have the same sides. Everything about them is identical. They're just in different positions or rotated. In similar triangles, it's a loosening of that. We don't need the sides to be the same. We just need the angles to be the same. So the relative positions of the sides is the same, but the relative sizes of the sides, the absolute sizes of the sides don't have to be the same. So this can also be contrasted, and I recommend highly you look up SSA and why that postulate isn't something that proves congruent triangles. It's because if you know the two sides and the exterior angle, you are almost there, but that setup admits two different triangles, an obtuse triangle and an acute triangle in most situations. And so we cannot rely on it reliably that it will prove that these two triangles are going to have to be congruent, in the same way that we can show that if the three sides are congruent and they form a triangle, then it must be the same triangle in a different position. So we're able to infer. So it's important stuff. Continue working on it. I'll see you next week.